Hi, I'm Reverend Greg and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. In this and the next few videos we'll look into blurring a sprite and a surface in a very efficient way. But why blurring, you might wonder? Why would I want to blur an image? Well, while blurring alone might be of limited use, it is essential for other shaders like a depth of field shader, bloom and glow, directional blurs, fake volumetric light, and probably many more shaders. So it's really important to every hobby shader programmer to know how blurring works and what the difficulties are. And it is a good way to exercise texture coordinates, to learn about getting multiple texture samples from inside the Fragment shader, and to use multiple render passes like in post-processing shaders. So it's really a great topic for any shader tutorial series. But in this video we're just focusing on a single pass blur to cover the basics of blurring. The rest will be explained in the next few videos. Single pass, by the way, means we're only using one shader to create the effect. But as you will see, this also means a huge performance hit when blurring. So in the next videos we'll cover how to improve the performance with multipassing, where we split up the blurring into a horizontal and a vertical blur to reduce the number of samples needed, using the linear filter of the GPU by picking samples between instead of on the texels, scale blurring by adding more render passes to further reduce the number of samples needed, hard-coded blurs to remove the calculation of the sample weights and offsets, and then we'll make use of that knowledge to create a bloom or glow effect. As always, a short disclaimer. This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistake in my video or see a better way to solve a problem, please add a comment so everyone can learn from you. If you want to learn more, and especially more maths on blurring, check the links in the description of this video. I'll link the kernel calculator, some tutorial videos and several articles, all of which are interesting views and reads and all helped me understand at least some basics of blurring. Downside: reading some of those articles made me feel really stupid and might do the same to you. Before explaining how blurring works, just two more things. Usually blur shader would be a post-processing effect because in most cases you'd probably want to apply a blur not to a single sprite, but rather to everything except the GUI. But since blurring a sprite is a tiny bit more complicated, and since this part of the tutorial series is mainly about coordinate systems, I'll start by blurring a sprite. In the next videos, however, when the blurring code gets more complicated, we'll switch to blurring surfaces, so we can simplify the code a bit and use the shader as a post-processing effect. And the other thing is this. While learning about blurring, I for the first time worked with a shader type that is very demanding on the GPU, and I realized the GameMaker variable FPS real is more or less ignoring performance issues on the GPU. I could get several thousand FPS real while the game was running in 10 FPS or less. That's why in the new base project I introduced a few videos ago, the FPS object won't only show FPS real, but also FPS and a progression bar for a quick visual reference. Now let's talk about blurring. I'll demonstrate blurring with this image. This is a small 7x7 blur. This is a 15x15. This a 31x31. And this is a 63x63 blur. As you can see, it takes quite high blurring numbers to really get a blurry image, and this will be a huge problem, as we'll see later. Now let's assume this grid represents the pixels in a small part of the image we're blurring. To blur the pixel in the center, we need to mix its color with the colors of the surrounding pixels. And if we do this for every pixel in the image, the whole image gets blurred. This grid from which we take color samples is called kernel. So here we see a kernel with a size of 7x7. That's the center pixel and 3 steps to each side. Since we're always going the same amount of steps to each side and also have a center pixel, the kernel size will always be an odd number. 4 steps to each side would be 2 times 4 plus 1 for the center, so the kernel size would be 9. And 5 steps to each side would be 2 times 5 plus 1 for the center, and so the kernel size would be 11. First, we'll create a simplified shader like this, where all pixels inside the kernel contribute to the final color by the same amount. This will result in a kinda cubic but still kinda smooth result, similar to this image. We're going to take a color sample from every pixel inside the kernel and add up the colors to mix them. But as we have learned before, adding colors means increasing the brightness. So we need to give each sample's color a weight, which basically determines how much a sample affects the final blurred color. In a 7x7 kernel, like seen here, we take 49 color samples, and thus in this simplified version, where all samples get the same weight, the weight of each sample is 1 divided by 49, which is about 0.0204. So to calculate the blurred color, we will add up all samples and just divide the result by 49. Here you can also see the main problem with blur shaders. A 7x7 kernel is quite a small blur, but we already need to take 49 samples for each fragment. In a full HD post-processing filter, this would already be 1920 times 1080 times 49 samples per frame. That's about 100 million samples per frame, and taking a sample is not coming cheap. Now to get rid of that blockiness and get a smoother result, we need another system to weigh the distribution. The farther away a pixel is from the center, the less it should add to the mix. The most common way to do that is applying the Gaussian equation. As you can see, the result is smoother, but it also looks a bit less blurry because the pixel farther away from the kernel's center don't count as much anymore. To increase the blur effect, we need to increase the kernel. So here we're looking at a 15x15 kernel. As you can see, we already take 225 samples per pixel. In a full HD post-processing effect, that would be about 466 million samples per frame. Not even a modern gaming GPU could handle that with 60 FPS, and a mobile would probably have several seconds to calculate just one frame. So again, we will need a better, more performant way to blur. But for this video, we'll stick to the inefficient way, and in each of the next videos we'll build on that foundation and add ways to improve performance by a lot. The difference made in each video will be stunning. But let's finally switch to GameMaker and start coding. Let's create a shader and name it Shader Blur 1 Pass ISO Weight Discrete. Then duplicate the template module from the base project and name it Object Blur 1 Pass ISO Weight Discrete. If you're not using the base project, just create a new object. But using the base project will let you follow along a bit easier. Then create a new child of the template room, name it Room Blur, and place the new object on the main layer of the new room. And while we're here, let's also change the kill modifiers of the base project. For now, we'll only need 2 sliders and no toggle or trigger buttons. So I will just stretch the kill modifier here to kill everything we won't need. Now in Create Event, we'll once again only need 2 regions, Title Info Corner Click and Sprite and Shader. So let's remove the rest. And as always, I start by adding some title and info text to the test module. In the Sprites region, I'll set up the sprite, shader, and 1 slider. As sprite, I'll just set an empty dummy sprite to determine the module size. Sprite dummy 256 by 256 pics. This has nothing to do with the blurring though, and really is just for the base project. But I'll also set up the sprite we're going to blur and name the variable sprite blur. I'll just pick one of the full screen images in the base project. Sprite photo sunset 1440 by 768. This one is as large as the view and thus perfect for our test. And as a shader, I'll set the shader we already created, Shader Blur 1 Pass ISO Weight Discrete. And we're going to need a slider to set the blur or kernel size. I'll set slider 0's caption to kernel, turn off the slider value drawing, and set the slider starting value to 0. Now for the shader we'll of course need some uniforms. The first will be for the blur steps to each side of the kernel, which will control the size of the blurring. The handle U blur steps for the uniform blur steps. The second uniform is for the weight of each sample. The handle U sample weight for the uniform sample weight. And the third is for the texel size. The handle uTexel size for the uniform texel size. The texel size is needed to tell the shader how far away from the current fragment to go in each blur step to get the next color sample. A texel basically is a pixel on a texture. The texel size can be easily calculated. We just need to divide the sprite size in UVs by the sprite size in pixels. GameMaker Studio actually even has two functions to get the texel size. Texture get texel width and texture get texel height. But since I already know we'll need UVs in a later step of this tutorial anyways, I'll just grab the UVs of the image and calculate the texel size from those instead of using those functions. First we need to grab the UVs like we did in the video on vignetting with UVs. Then we also need the sprite size in pixels. Image width is sprite get width of sprite blur, and the image height is sprite get height sprite blur. And finally we can calculate the texel size from the UVs and the pixels. So the texel width is the sprite width in UVs divided by image width, and texel height is the sprite height in UVs divided by the image height. In case you wonder why I'm getting width and height of a texel. A texel is a square on the texture page, but its coordinates might not be. In the shown example I just picked a random texel size of 0.001. If the texture page is a square, both texel width and height are the same in UV space. But if the texture page isn't square, then the texel size won't be either, since the UVs of the texture page always go from 0, 0 to 1, 1. So let's say the texture page is twice as wide as high. Then the texel's UV's dimension will be half as wide as high. That's it for the create event. And we won't need the step event, so let's just delete that. Over the next few videos we'll create several more modules. To get them all to work nicely together, I want to draw the test module frame and text in draw GUI event. So let's create one and add the script for the module drawing there. By the way, again this is just needed for the base project and not for the shader per se. Now the draw event. First let's prepare some local variables we'll need. The first being blur steps. I'm going to use slider 0 of the base project for this. Var blur steps is round slider get value 0 times 31 plus 1. Blur steps will be the blur steps to each side of the calculated fragment. Slider 0 returns a value from 0 to 1. So this line will return integers from 1 to 32, and thus the kernel size will go from 3 by 3 up to 65 by 65. If you're not using the base project, set up a slider of your own or hardcode a value. Less than 3 blur steps is only a very small blur, and more than 15 might already get your GPU's fan speed up audibly. I have absolutely no idea if you could fry your GPU if you run a demanding shader like this for a while. So don't go too high in your experiments unless you know more about hardware than I do. I ran this shader with a kernel size of 200 for a minute, which is a lot, but my GPU fan was as loud as never before, so I got kinda scared and limited the kernel size to 65. Next we'll need the kernel size and the total number of samples, which in this shader version is just a squared kernel size. The kernel is blur steps times 2 plus 1, so each side and the center, and kernel squared is kernel squared. Now since we're going to add more base project modules to the same room later on, but want only one to draw at any given time, we'll make use of the global variable selected module in the base project. This means the code in the if statement will only run if this module is currently selected. And inside the if statement we can now set the shader and its uniforms. The blur steps we got from the slider. The texel size we already calculated in create event. And as I showed in the introduction of this video, sample weight for the first shader version is just 1 over all samples in the kernel, so 1 over kernel squared. To draw the image, I'll just draw the sprite to 0, 0. The sprite I'm using is of the same size as the view and its origin is at 0, 0, so this will cover the whole view. And we can remove the script draw module here because we're calling that in draw GUI event already. But I would like to add some dynamic info on blur steps, kernel size, samples taken per fragment, and samples taken for the whole image. In later videos we can then see how much the code improves. So to set the text, we can just set the variable corner text to whatever string we want to draw. Samples per image is the kernel squared times image width times image height. Corner text is the blur steps plus the kernel plus the samples per pixel plus the samples per image. With all that set up, we can finally get to the shader. We won't need the vertex shader, so just close that. In the fragment shader, we'll first grab the uniforms. Blur step is a float, texel size a vec2 since we pass in a width and a height, and sample weight is a float again. Then inside the main function, we'll set up an empty vec4 color. Vec4 blurred color is vec4 0.0. We will fill that with the sum of all sample colors, and in the end we'll pass the result to glfrag color. So glfrag color is the vertex color times blurred color. As mentioned, we'll just add up all colors to mix them and reduce the luminance by applying the sample weights. The easiest way to do that is by multiplying the sum of the samples by the sample weight. Now the samples. Normally in a shader we call the function texture2d once only to get the sample color of the texel at the current fragment's location. But as mentioned in the introduction, we'll need to take samples from the surrounding texels as well to get the blur. We'll do that using offsets in the x and y or u and v axis of the current fragment and calling the texture2d function for those offset coordinates as well. So we'll need two local vector2 variables, vec2 offset and sample. Offset will be used in a for loop to get the samples to the left, above, the right and below the fragment we're currently calculating. And sample will be the UV coordinates of those samples. So let's create a nested for loop to step through all samples. First a for loop in the x or u axis on the texture page. For offset.x is minus blur steps, until offset.x is smaller or equal to blur steps, and offset x increment. This means we're starting left of the fragment and move to the right, incrementing the position by one blur step on each loop. With blur steps set to 2, we'd go from -2 through -1, 0, +1 to +2. Then we set up the same for the y or v axis. So this nested loop loops through each tab in the kernel from the left to the right and from the upper row down. Now we can take the color of each sample. To do this, all we need to do is calculate the position of the sample on the texture page by multiplying the offset with the texel size and adding that to the texture coordinate of the current fragment. Then we grab the color from that sample with the same function as usual, texture2d. We want the color of GM base texture at the sample's coordinate and we add that to the vec4 blurred color. So texture2d can not just get the color of the current fragment. By changing the position of where to take a sample's color, we can get any color on the texture page. Now these for loops and what happens within might be a bit tricky to completely understand since we're working with floats and vectors at the same time. If you feel like you're not fully understanding this code despite knowing what it does, then I strongly advise to watch the video Introduction to GLSL Part 2 in this video tutorial series playlist. A link to the playlist is in the description below. That whole video is about working with floats and vectors. And for those who watched that video, here's a quick reminder. Multiplying, dividing, adding and subtracting vectors with vectors or vectors with floats always works component-wise. So now that we got our first blur shader, let's run this in debug mode. Increasing the slider a bit starts to visibly blur the image. Increasing it more shows the blur is a bit blocky, smooth but still kind of blocky. Increasing the blur steps even more lets the GPU fan howl up a bit already. And if I pull the slider all the way to the right, you'll see a significant drop in the frame rate. Just watch how the progression bar on the right side slows down, and after an additional full cycle, it'll show how low the FPS gets. So we're at a pretty low FPS now with a kernel size of 65. The shader is taking nearly 4 billion samples per frame and cannot keep up at all. But there's another thing we can observe. The blur on the right side is wrong. There's a dark area there that shouldn't be. Pausing the debugger and checking the textures shows what's happening. This is the sprite we're drawing. And to the right there's another sprite. In this case the same motif but another sprite anyways. So our blur shader takes samples on the texture page from the sprite on the right and blurs those colors into the fragment. Depending on how your texture page is built, it might be other sides, but chances are high at least one side is wrong. So we need to find a way to prevent this color bleeding. The easiest way is to clamp the samples to the UVs of the sprite, so no sample can be taken from outside the sprite's UV on the texture page. This will reduce the blur on the edges, but as you'll see, it's not that bad. So back to the object's create event. To clamp, we'll need those UVs now. So let's create another handle, UUVs, for the uniform UVs. And let's already store those in an instance variable because they won't change after compiling. So I'll create an array with the left, top, right and bottom UV. The reason why I'm not just turning UVs all into an instance variable is because I'd like to pass the UVs as an array to the shader, and UVs all has more components than I need. UVs all has 8 components and I just need the first 4. In draw event we'll now just need to pass the UVs array to the shader. In the fragment shader we'll need to grab the uniform UVs, and since we pass in an array with 4 components, we'll set it to a vec4. And now all we need to do is clamp the sample coordinates to the UVs of the sprite. So to UVs XY and UVs ZW. So we're clamping the sample position to the top left and bottom right UVs of the sprite. And since clamp can be used component-wise with vectors if all arguments are of the same data type, we can do this in one line, clamping the U component and the V component in one function call. Again, if you're not understanding how this works, really watch the video introduction to GLSL part 2. In this case, maybe also the video on the Syncity shader effect, where we had a similar situation in the mix and power functions. Now let's run this again and max out the kernel size once more. As you can see now, there's no bleeding at all. And in my opinion, it's hardly noticeable that the sides actually blur less due to the clamping. But let me show you what happens if I run this on my tablet. The first thing noteworthy is how much slower this shader is on the tablet. But if I move the slider far enough to the right, you'll start to notice unexpected changes in color and alpha. The reason lies in the size of the kernel and the variable precision. Precision describes how many digits behind the decimal point can be stored in a variable. So the larger the kernel is, the lower the sample weights get. In fact, they get so low that the standard precision of vectors on Android and maybe iOS as well lose necessary color information. Now it seems on Windows the standard precision is set to high precision for floats and vectors since everything worked fine there. But on Android the standard precision for vectors seems to be either medium precision or low precision. Actually, I'm not absolutely sure if that's really true. It's just the only explanation I had for myself on creating the shader. If anyone knows for sure, I'd love to hear. Just leave a comment beneath this video. Fortunately, we can easily fix that though by forcing a high precision on the vec4 blurred call by writing high p in front of the variable definition. So whenever precision is not a real problem, you can set a variable to low p. And if low p is too low and high p too much, you can also set medium p. Now running this on my tablet again, you can see this bug is fixed. But now let's get rid of that blockiness by changing the weights to Gaussian weights. Since I want to be able to compare both, I'll just duplicate the object and name it Object Blur 1Pass Gauss Discrete and place it on the main layer of Room Blur on the second orange slot. I'll also duplicate the shader and name it Shader Blur 1Pass Gauss Discrete. In Create Event, I'll change the info text and set the shader to the new shader. Before going on with coding, let's have a quick look at the Gaussian equation. This is the equation we'll be using. S stands for sigma. In this version of the shader, we'll be using the two-dimensional equation on the right side, which basically is a squared version of the one-dimensional equation on the left. When we get to multipassing in the next video, we will use the one-dimensional equation on the left side. And in both single-pass and multipass shaders, we're going to use the simplified versions below instead of the correct versions on the upper row. If you understand this equation just by looking at it, congratulations! And why are you watching this video? But if you don't understand this equation, one thing noteworthy is that every variable is squared. So a negative x or y offset or a negative sigma will always result in a positive number, and squaring usually means the result of the equation is not linear but curved. Another thing I should explain is the function exp. This is just a function to raise e to the power of whatever is in the brackets. And the last thing I can explain is this. If we have an x and y of 0, this would be the center pixel of the kernel. Then the term inside of the brackets is 0 as well. And anything to the power of 0 is always 1. So the weight of the center pixel will always be 1. And the fact that the term in the brackets is always negative except for when it's 0 means the result of x will always be larger than 0 and smaller or equal to 1. The larger x and y are, the smaller the results will be. So the farther away from the center a pixel is, the smaller its weight will be. But that's pretty much everything I can tell about this equation because I don't understand more than that. But I can show you what it does in Desmos. In case you want to experiment with the equation yourself, I'll provide a link in the description of this video. So this is the one-dimensional Gaussian equation with a sigma of 1. The y-axis shows the result of the equation based on x, and x basically is the offset of our kernel samples. The further away the sample is, the lower the returned weight of that sample will be. The red line shows the Gaussian equation and the green line the shortened version we're going to use. You can see the difference in the result is mainly that the maximum of the shortened version is fixed to 1. So the center texel's weight will always be 1 and everything else will be less than 1. If we increase sigma, the shape widens. This means we're getting closer to the isolated version we already created, and this of course also means the result will look as blocky as well. That's simply because there's hardly a difference in weights between the center and the border of the kernel. It's easy to understand that if you think of the blue box being the kernel. Now if we decrease sigma too much, we'll reduce the blur effect because the sample weights drop to 0 before reaching the kernel's edges, which means the outer samples won't contribute to the result and are just wasted. What we usually want is a curve where the weight of the farthest sample in the kernel is something above 0 still to get a wide blur, but also where the weight of the farthest sample is not too far above 0, so we won't get a blocky result. And this is about what the two-dimensional equation would look like. If you imagine the sprite being the base of this grid and the height of the grid being the weights of the sample, you can get a pretty good idea of how the Gaussian equation works. Now back to coding. We won't need the uniform sample weight anymore, since it's not going to be the same for each sample. We will have to calculate that inside the fragment shader now. But we will need a new uniform sigma for the Gaussian equation. So let's delete uSampleWeight and add uSigma for the uniform sigma instead. The rest here can stay the same. In drawEvent we'll get sigma from slider 1. But the sigma of 0 will result in a division by 0 in the Gaussian equation. So I'm going to set a minimum value to just above 0. And the sigma of more than 1 won't make a real change anymore. Inside the shader block we can of course remove the line setting the sample weight and pass in the sigma instead. Also in this shader version we will need the local vars kernel and kernel squared for the corner info only, so I'm going to move them to the lower part of the drawEvent where we set the corner text. The last thing to do in the drawEvent is adding sigma to the corner info box right after the kernel. Inside the fragment shader we can now add the sample weight calculation. First let's also remove the uniform sample weight but add the uniform sigma. Sigma is a float as well. Then I'm going to add a function for the Gaussian equation. We've used functions before in the video on brightness, contrast and saturation, so I'm not going to explain here how functions in GLSL work. The sample weight will be a float. I'll call the function weight, and looking at the Gaussian two-dimensional equation, we'll need two variables to describe the position of the sample, the u and the v coordinate. So we'll pass in a vec2 for those. Now we can just copy the simplified two-dimensional equation. Inside the main function we'll need to add two new floats. Float sample weight will temporarily store the sample weight. And total weight will sum up all sample weights and will be used to keep the luminance of the pixel by dividing the sum of the sample colors. As with the blurred color, we need to initialize total weight to 0. And in this version of the shader we'll also need the kernel size. So let's add another float kernel and set it to 2 times blur steps plus 1. This could be moved to the vertex shader and passed in as a varying float, or moved to GMS and be passed in as a uniform. But I'm just going to leave it as it is. Inside the nested for loops we'll grab the weight of the sample, calling the function we just created. But we're not just going to pass in the offsets because they're an integer from minus blur steps to plus blur steps, and we need a value in relation of the kernel, so it works for any kernel size. Luckily it just so happens we just calculated the kernel above the for loops, so let's divide the offset we pass in by the kernel size to express that relation. Now we can add the result to the total weight so we can equalize the luminance in the end. The sample line can stay the same, but at the blurred color line we now multiply the color with the sample weight. So we're setting how much of that sample's color should be added to the sum. The last thing to do here is dividing the sum of the blurred color by total weight to keep the brightness. Now I just need to fix some mistakes you probably all saw already. First is the weight function. The attribute is of the data type vec2, of course. The second is in the drawEvent. At the end, samples per image needs to be set after kernel squared, since it's using that variable. And finally, I forgot to set up slider 1 in createEvent. Caption is sigma. I don't want to draw the value, and I'll set the starting value to 0.5. But now let's run this one last time. First let's increase the blur steps a bit and sigma. As you can see with the high sigma, the result is as blocky as in our isolated version. But if we slowly decrease sigma to about 0.6, the result starts to be acceptable. We lose some of the blurriness, but the quality of the blur is much nicer. We can further decrease sigma a bit to like 1/3 and get a really nice and smooth blur. but calculating the weights for every sample in the Fragment shader came with a price. Now our shader code is even more inefficient, and by quite a lot. If I set the kernel size to the maximum, you can see how slow this shader now is. The main problem of this blur shader though still is the sheer number of samples taken. If we can reduce that, then the performance hit of the weight calculation will be reduced as well. A second problem in my tests was that this version reliably crashed the program on my tablet when setting the kernel size to the maximum of 65. I'm not sure why, but I didn't care much because running a game in less than 1 FPS is not an option anyways. But enough already for today. We will fix those problems in the next videos where I introduce multipassing, linear texture interpolation, scale blurring and hard coding a blur. Until next time.